Oh boy, second to last live stream. So, got two emails basically asking the same questions, and these are the review packets for the new organic material. And I do see the question in the chat. I'll get to that after I do the characterization problems. So I did get one specifically for the last page, and you've got this double dehalogenation, or potentially a dehalogenation, this compound. It says you have an organic base and you have a newly synthesized organic catalyst that's reacted with 2,3-dichloroheptane to determine its viability as a reagent for making alcohols. Based on the FTIR spectrum, will this work as a reagent for making alcohol for the halogen alkanes? And this is actually something you commonly see people trying to do, where they synthesize a new catalyst and hopefully it's supposed to do what it's supposed to do, but generally what they find is that sometimes it doesn't, or it doesn't give great yields. And so they claim that they've reacted it with the catalyst, and they want to know if it made the alcohol. So if you look at the IR, you see this, and your peaks here, these are your CH3, CH2, CH bending modes. They will also contain halogens. You really can't figure out if you have a halogenated alkane based on the FTIR. It's just the shift for those bending modes is really small. But the big thing we're not seeing here is the bending mode at 3600. So if you look at that figure on the last page, you see a nice, beautiful picture IR of an alkane, but you don't see an alcohol. And so the conclusion here is that their catalyst didn't work. If they had produced an alcohol, what we'd expect to see is the H bonding modes. So with alcohols, particularly small alcohols, this isn't necessarily true for very large alcohols, but for small organic alcohols, typically we see a bending mode about 3600. It's a big, fat, broad peak. It corresponds to hydrogen bonding, which is what alcohols engage in. So what we can say for the last one is that based on an IR spectrum, their catalyst does not work. So let's go through the characterization problems. So the first one, for the following reactions, compare the characterization of data products to determine what was formed and isolated during the reaction. So for this one, for the first one, we have Cl2 with benzene, and we're trying to figure out what we produced. And so we have three options here. So those of you going on to organic chemistry, organic 2 chemistry, this is the ortho meta para, or the 1,2, 1,3, and 1,4 dichlorobenzene. And when we look at the NMR spectrum, the question is, how many peaks do we see? So in this NMR spectrum, we see an integrated area of 4. There's only one peak. So there is only one unique functional group underneath NMR. So if we look for mirror planes here we'd expect to see 2 NMR peaks. One's corresponding to these two positions and one corresponding to these two positions. If you look at this one, we expect to see 1, 2, 3 peaks. With this one, we see 2 mirror planes. So this and this, these two are the same because of the left-right symmetry, and these two here are the same by up-down symmetry. So this only has 1 peak. So that's all this question is getting at, is like, do you see under NMR how many different functional groups there are? And in this case, we expect to see 2, 3, and 1. So this is your answer because it's the only one that would produce one unique NMR signal. Oh boy. Next one, you're given N-bromosuccinide and you're asked about the reaction. And you can get So this one's a little hard to see, but what you're looking for is how it changes. Sorry, it's kind of tiny on my screen. So if you look at the area, we have beginning areas of 2, 3, 1, 2, and 2. And what we're trying to figure out from the 1H NMR is where these different things are. So in NMR, these two would be the same. These two would be the same. This would be a chemical shift. This is a chemical shift. This is a chemical shift. Chemical shift. So we have 2, 2, 1, 2, 1, 2. So where is it getting the 3 from? I know with this one, what you're trying to do is you're trying to compare the starting and final signals to see which signals have changed. I wouldn't worry about that problem. Let's go to the next one, carbon-13, and we want to know if we do elimination or if we produce the alcohol. And we're looking at the carbon-13 NMR, and this is going to be another one where we're trying to figure out how many unique peaks there are in the NMR. So we know we take a hydroxide. Actually, no, with this one, you don't even have to count the peaks. Okay, so on page 40, if you look at those two peaks at 110 and 145, there is only one type of functional group that will give you that type of long, deep shift. So if you look at A, B, and C, or let's look at B and C for that one. So we have these potential products. And if you go to test tables, so these are available, these will be supplied to you for the final exam. And we look at shifts of carbon-13 shifts. So your alkane groups, CH3, CH2, CH, these sit in the 0 to 35 ppm range. Your alcohols, where are you? Carboxylic acid. Alcohols, ROH. These are going to sit in the, just saw it, 50 to 65 range. Your double bonds, so R double bond R, 100 to 150. So with this one, if you just look at the chemical shifts, what you'll see is that you've got two peaks here, one at 112, one at 145-ish. The only way you can get those two peaks is if you have an alkene. So that's the tip off here that you have an alkene, is just where those chemical shifts are. Based on the EIM, how many times did Cl substitute hydrogen on the starting compound? So question is, if we get substitution, so how much does this weigh to begin with? 1, 2, 3, 4, 5, 6, 7, 8. C8, 5, 8, 10. So 8 times 12, that's 96. So this weighs 186 AMUs. Now the question is, how many times did we get substitution on this? Well, to do that, we just start counting the weights. So every time we do a substitution, we lose a hydrogen and we add a chlorine, so that's going to add 34.5 AMUs to it. So if we get one substitution, this should put us at 140.5 AMUs. If we do two substitution, that's 175 AMUs. If we do three substitutions, that's 209.5 AMUs. Now, if we look at the mass spec, the mass spec has peaks above 160, so that one's not a possibility. It's got a peak above 200, so that's not a possibility. If we did quadruple substitution, that would be 245. And our spectrum doesn't go to 245. So here we have triple substitution. And the triple substitution is just counting up the weights. Every time we substitute off one of the hydrogens with the chlorine, we lose the weight of the hydrogen and we gain the weight of the chlorine. Chlorine here is 35.5. Hydrogen here is 1, so that nets us 34.5. So what I did was I took the parent weight, and for monosubstitution, figured out what a weigh, di, tri, and quadruple substitution. So whatever we have here, it's a triply substituted product. And that gets us to page 42, which is our answer at the start. All right, now the chat. Can I get help on last week and this week's discussion board? So let me bring up the discussion boards. All right, so last week's discussion board. And a reminder for all the sections, you have until Wednesday at midnight to complete the discussion boards. Thursday, I'm going to grade the discussion boards that have been submitted. Beyond that, there is no way to make up the discussion boards. We're kind of getting to the point in the semester that we need to get final grades in. And so what I want to make sure of is that grades are pretty much done by Friday, if not Monday. If you're taking 151 and you're doing your exam through the ELTC, I'm not going to get your exams until Monday. So Monday, you'll start seeing the final grades for Chem 1 posted. Orgo 1, you're definitely going to have your grades up and posted by Thursday. So the plan here is to have all the grades done by Monday. If there is any need to contend a grade, that will give you through Tuesday of next week. Wednesday, I need to start submitting grades. It is a practical issue. It is not a policy. In the semester, all professors submit their grades to the servers. The servers have a bad habit of not being able to handle all those grade submissions at once. So we submit on Wednesday, if not earlier, might do it Tuesday night, to ensure that if it gets submitted to the server but the server doesn't register it, we have time to resubmit your grades. So this is why I'm trying to get all these grades out of the way right now, is that if there's any need to contend a grade, you'll have a window over which to do it. And then I'll also have a window over which to submit your grades to ensure they actually get submitted to the registrar's office. Anyway. Problem asks you, first of all, to name product 1, product 2, and 2, to figure out how to make product 1 from the starting reagent, how to make product 2 from product 1. So in terms of the reagents, these are both 2 steps, brominate and eliminate. So what does the bromination do? What the bromination is going to do is give us the dye substituted. You need the dye substituted in order to do 2 eliminations. If you just did HBr, you would get right back to the starting alkene, probably with a cis-trans mixture. So your first step here with the bromine gives you the dihalogenated form. Then we have the NaNH2, NH3. A purist will sit back and say you need to acidify for this step. Not really, but for this will give you the 2-butene. Now, second step looks exactly like the first. We do the bromine, and we do NaNH2 with NH3, and this one you should probably actually do an acid workup to put the protons back on the end. What's going to happen here? We're going to get quadruply substituted halogen. You can't just do 1 bromine equivalent, you need 2. This is going to serve 2 purposes. 1, we need 2 bromines to eliminate off each end. The second is that this ensures that there's no hydrogens on these two carbons, so when we do elimination, we don't return back to our starting alkyne. So if you just did monosubstitution here, when you did elimination, that bromine would pop off, and probably that one too. So you would end up just getting back to your starting butane. So we need the disubstituted product, or the quadruply substituted product, and then we do the double elimination. If we don't acidify, we'll probably end up with the hydrogens coming off the end. But I didn't take off credit if you didn't do the acid workup. As for 2, 1, 3, buta, diine. Now for the discussion board this week. Name the ethers that are formed by the following acid catalyzed reaction. This is an issue with the acid catalyzed ether synthesis. It is awful if you want to do asymmetrically synthesized ethers. This is where your Williamson ether synthesis is a lot more powerful. So, any ether synthesis will yield you, if you have 2 alcohols, will yield you a mixture of whatever R and R prime are. But R and R prime can be either ethyl or propyl. So in the case that R equals R prime, meaning that we have self-ether synthesis, we end up with the diethyl ether and the dipropyl ether. Now, if R doesn't equal R prime, meaning that we have 2 different alcohols, this is where you end up with the ethyl propyl ether. So there's 3 products that are formed by this acid catalyzed reaction, 2 self-made ethers, and then 1 ethyl propyl ether. And again, this is the limitation of acid catalyzed ether synthesis. It is awful for the formation of, it's not very selective for asymmetric ethers, meaning that both R groups aren't the same. Now, that said, the Williamson ether synthesis, I find it interesting because from a practical standpoint, you would never do it industrially. So for the Williamson ether synthesis of this, you would react your propanol with sodium to give you propoxide, and this would ensure that you got this for the majority. The problem is that sodium here is a super reactive metal. And so, yeah, you would have an easy time of separating out the products, but this is a particularly energy intensive step. Really what would happen is that you would do the acid catalyzed. So we'd start out with our 2 ethers, we'd run it into a reactor with an acid catalyst, and then we'd run it to a distillation column. And we'd get 3 cuts. We'd get the lightest ether, which is the diethyl ether, the lowest ether, which is the dipropyl ether, and then we would be able to isolate back out our ethyl propyl ether. And these, we would just feed back into the reactor. So you may have a washing step where you hit it with a little bit more water, but honestly, it would be easier to run these with distillation, or basically just keep feeding the ethers back in instead of trying to like do a Williamson ether synthesis. But anyway, that's it for questions. Again, we only have 1 more live stream. That is tomorrow. That is the end of the regular semester. Final exams are going on this week for both Chem 1 and Orgo 1. Again, the goal for Orgo 1 is to have your grades posted by Thursday, and then we can start seeing if there's any grade contention. I'll tell you right now, if you've got like an 83, I'm not bumping you up to an A. If you're within a point of the next letter grade, that's when you kind of have a bit more of a case to argue. But if you've got like an 87, I'm not giving you 3 points. But something like an 89, there's a little bit more room there because you are pretty close. But anyway, these are not lessons, these are not lectures, these are office hours, so I've got some questions being asked of me on Teams, so I'm going to get to those. If you have a question, please post them in the chat, and I'll get to them as soon as I can. All right, just got a request to go over number 10 on the old material homework. So let's open it up. What is the major product of the following reaction? So B2H6 diglyme H2O2 NO2. This is hydration, and it's hydration in an anti-Markovnikov fashion. So this is your starting reagent. And if we just added water, H2O, we would probably get this as the final product. There is potential for a rearrangement to give you this as well, but that's assuming you're working water. The hydroboration oxidation, B2H6. There's like a dozen other things that go into this reaction. H2O2, NaOH. This is actually going to give you the opposite. So it should be, of course in my case it's A, but that should be the product you get. So this falls underneath our anti-Markovnikov rules. So Markovnikov addition, we'd expect the OH group to go to the most substitute carbon. Your B2H6 here sends to the OH. The way I remember it, if we do peroxides with HCl or any of our normal additions, we always get anti-Markovnikov. Now that's a situation where you're right for the wrong reasons. This is actually not what makes it anti-Markovnikov. This is what makes it anti-Markovnikov. But if you just remember, if you're seeing the H2O2, it's probably an anti-Markovnikov reaction. That helped me quite a bit in undergrad. Oh, that one. Okay, that's number 1 on mine. Pure sample of S-phenylalanine. Big rotation 7, and the mixtures have a rotation of 7. What are the percentages of R and S in the enantiomers? So actually this isn't too bad. So your EE here is your measured rotation over your specific rotation. So this is 7/70, which is 0.1. Your percent EE in this case is going to be 10%. So what that tells you is the R minus the S here equals 10%. And that means whatever ratios you're given, the difference has to be 10%. So if we look at the 4 answers, there's 95, oh, I'm sorry, the S and the R in this case. If you're given 95% and 5%, that'll give you 90%. That doesn't match the 10%. If you're given 52.5 and 47.5, that's 5% EE, that doesn't work. You're given 90 and 10, that's 80 E, that doesn't work. So the last one it has for me is 55 and 45, so that's your EE of 10. So if you just take the ratio of the measured activity divided by the reference, that's your percent EE. And then you're just going to look through those ratios to figure out which one actually gives a 10%. Looks like it's scattering the questions, randomizing the questions. How odd. Yeah, you're welcome. So I got a question. There's a course entry thing that says tutorial quiz that was actually for when we were still doing lab reports at the start of the semester. So every instructor has different expectations for how to write lab reports. I actually have a writing tutorial that will like walk you through the process. And you were supposed to take two tutorial quiz before you did the first lab for the first lab report. That said, basically, like we never did lab reports. So because of that, that tutorial quiz is just kind of an artifact of from the start of the semester. It's not being counted for anything at this point. The only thing that gets counted for your quiz grade in the lab is the safety quiz. Yes, so for the virtual lab submissions, you just need to do a screenshot of the final grade. I haven't figured out how to make SolveChalk actually talk to the grade book, and at this point, like, there's no point. So just take a screenshot, upload it. The 1-bromobutane, there is a glitch, or there's a bug with that particular module. It will only do points out of 85. There is a way to fix it, but it requires me to completely reload the module, and it's just not worth it, so I've been grading out at 85. All right, if you got a quick question, I can hang on for a couple more minutes, but I do have other things I need to do this morning. So I'll be on for like another minute or two, and after that I need to sign off. So the alkynes and ethers are going to be like a very, very, very teeny tiny amount of this final exam. It's weird because it's in the course SLOs, but it's not assessed well on the final exam. So the alkyne ether work is more prepping you for organic 2. I would say definitely focus a lot more on test 1 through test 4. You're going to see a lot more questions. In terms of mechanisms, E1, E2, SN1, SN2, those are the bigger mechanisms to memorize. All the other ones like ozonolysis, and the transition metal catalyzed stuff, you don't need to know their mechanisms. Those are speculative at best, and they don't show up on the final exam. But yeah, those would be the big ones. And then particularly with SN1, SN2, E1, E2, the reverse them. So Markovnikov, anti-Markovnikov, what are examples of Markovnikov and anti-Markovnikov reactions. All right, I need to get going. So one more live stream tomorrow, 11 to 12. Final exam is Wednesday for Organic 1. And then for folks in Chem 1, Wednesday through Friday, that's your test window. If you have not signed up, I would highly advise you to go right now and go sign up at the ELTC, because their slots do fill up. And a lot of instructors are giving their final exams this week. So I will see several of you Wednesday.